Wanted to go into a little more detail about the AM radios because I think this is kind of neat. It's an interesting application of practical resonance. So the way it works is that an AM radio is basically an RLC circuit where the resistance and inductance are fixed and the capacitance is adjustable. In fact, the knob on the radio that you tune is typically an adjustable capacitor. So a signal broadcast at frequency omega acts effectively as an input voltage with that frequency omega to the tuning circuit. And then the resulting steady periodic signal or particular solution in the tuning circuit drives the amplifier, which is what you hear. So what you hear ends up being proportional to this expression right here. So there's what the amplitude envelope looks like in the electrical situation as opposed to mechanical. And so you see we've got the resistance over here. This other part off to the side, this is called the reactance. It's the imaginary component of resistance, which is a fun way to say that it's the resistance due to alternating current, the sinusoidal activity. And then this, in the entire combined effect of all of this is called impedance. So if you've ever heard of impedance, that's what it refers to. And so the one part of all of this that we can change is this capacitance right here. And so by tweaking C, we can change how the thing is tuned. So we want to choose C to maximize this amplitude. Okay, so let's see. Well, then we want to make omega L minus 1 over omega C go to 0. So that's what we're trying to match. And so then that means we need C to be 1 over L times omega squared. And then in this case, the amplitude that we have, let me just recopy that expression. Oh, it's a mess. Becomes just equal to E naught over R. And so when you tune the dial, you're setting the capacitor to this value. But there's actually a little bit more to it. So modern AM radios also use a second capacitor. And it's set at around 455 hertz higher than the desired frequency. And this produces a beat frequency that boosts the signal even higher. And that's better for amplification and for selectivity. So if we look at, let's see, so going back to, suppose we have our mechanical oscillator, well, at least in terms of notation. And we find from it that the transient component of the solution is, let's see, so F naught over M phi squared minus omega squared cosine omega t. Then if we take initial conditions to be at rest in equilibrium, like so. Then the steady periodic part is going to look like f naught over m phi squared minus omega squared cosine omega t minus cosine phi t, which can be rewritten using a trig identity as sine of phi minus omega t over 2 times sine of phi plus omega t over 2 by standard trig identity. And so then if phi is pretty close to omega, then phi plus omega is much larger than the difference. So this sine function oscillates much faster than the one with the difference. So we can think of this then as being something that has now an amplitude envelope that varies sinusoidally. So here, the amplitude A is the rest of that stuff. So f naught over m over phi squared minus omega squared sine phi minus omega t over 2. Okay, so the picture that goes with this is as follows. Come on. Okay, so if I graph A, then that's the one that's going to be going slowly. So it will be going like maybe like this, and then so that's going to be my amplitude envelope, and then so the actual signal, which is oscillating very quickly, will be looking like this. And so then you can see that beat frequency that's being given by the A function.